Hello. Hi. So today we have Varun Shah from IISER Pune, and he'll be talking about what irreducible representations are dimensional. Before we begin, let's recall our three guidelines. Everyone has something to contribute, no one has all the answers, and we are all learning. So with that, Varun, take it away.
Hi, yeah, thanks for inviting me. So today I'll be talking about what irreducible representations are odd-dimensional. This is something I've been thinking about this year on and off, and I thought, let me just tell people about it. It'll make me more confident in whatever little I have till now. So here we go. Uh, yeah, yeah. Okay, yeah. So let's start with the warm-up for the question. So let's look at binomial coefficients. And we can ask, when is the binomial coefficient n choose are odd? So for example, if n is 30 and r is 5, we can calculate 13 choose 5, and maybe I should have actually done the calculation here. But yeah, we can calculate 13 choose 5 and see that it's odd. On the other hand, if you calculate 13 to 6, you'll see that it's even. So is there a easy way to look at to take n and r and deduce if it's even or odd without actually going through the computation? So one cute way is this. We can represent 13 by 13 balls, and we can partition them into circles. The first one has 8 balls, the second one has 4 balls, and the third one has a single ball. And these are the powers of 2 that show up in the binary expansion of 13. So 13 is 8 plus 4 plus 1. Now, if we want to, so what is 13 choose 5? It counts the number of ways to choose 5 of these 13 balls. And so this is one way of choosing 5 balls out of these 13 balls. And here note that the circle with 8 balls and the circle with 4 balls, they are partially filled. So I'm denoting a ball chosen as filling up the circle. So yeah, if we have this configuration, then here 2 of the circles are partially filled. So partially filled circles, they can be rotated. So here we can rotate this 8 times, and then we come back to its original spot. So they contribute an even number to n choose r. Okay. On the other hand, if you have a filling like this, which is also a choice of 5 balls out of the 13, rotating any of these does not change the configuration. So this only contributes 1. Now, this kind of filling is a very special one because here so 5 is 4 plus 1, right? And luckily, 13 also had a 4 circle and a 1 circle for us to completely fill those. So we deduce that the binomial coefficient is odd if and only if the powers of 2 that occur in the binary representation of r also all appear in the binary representation of n. So again, for example, here this worked well because 13 is 8 plus 4 plus 1 and 5 is 4 plus 1. But if we had 6, then it would, so 6 is equal to 4 plus 2. And there is no way to choose circles, no way to choose 6 circles out of 13 so that choose 6 balls out of 13 so that this so that each circle is either completely filled or completely blank. Okay. And we also deduce that the number of r for which n choose r is odd is equal to 2 to the a of n, where a of n is the number of ones that appear in the binary representation of n. So yeah, again, because what we want so the condition r for n choose r to be odd is that the powers of 2 that appear have to be a subset of the powers of 2 that appear in the binary representation of n. So we just need to choose, we need to choose a subset of them. So yeah, we can enumerate this. So this was a warm-up. Now, the talk is about parities of degrees of irreducible representation. So why is that interesting? So yeah, one reason why I got into this is because of spinoriality. So an orthogonal representation of a group is said to be spinorial if it lifts to the pin group. What that means is that let's say we have a group G and we have a representation pi, which is orthogonal, which means that it maps into some orthogonal group. Now this orthogonal group has a topological double cover, which is the pin group, and we want to ask if there exists a homomorphism from G into the pin group that makes this diagram commute. And if that happens, then pi is said to lift to the pin group, or it's said to be spinorial. Now, recent work for many groups has shown that spinoriality of a representation is often governed by the parity of its character values, especially the dimensions. For example, when we are looking at Lie groups, if you're not just the parity, it's governed by the dimension or the character values being highly divisible by power by 2. What that means is that for all families of simple Lie groups, if your dimension of the representation is divisible by a large enough power of 2, that's enough to guarantee that your representation will be spinorial. And this comes from the fact that spinoriality is related to certain certain classes in the mod 2 group cohomology of the group vanishing, and that's why parity and spinoriality are related. But again, this talk is about combinatorics, so this was just a single slide. I'll move on to combinatorics. So why is it interesting to combinatorialists? So as we saw for the binomial coefficients, answering questions of parity can be done by nicely grouping up objects and then arguing that everything's grouped up into groups of even size, while there's a single one that's left, and that is enough to deduce that the total number of a family of objects is odd. So what happens is that a lot of irreducible representations of a lot of families of groups are indexed by combinatorial objects. The dimensions of these representations can be interpreted as solutions to some counting problem. So for the symmetric groups, this is counting the number of standard fillings of a Young diagram. I'll define what they are in a minute. And for the general linear group over the complex numbers, it's counting this number of counting the semi-standard fillings of a Young diagram. So counting these objects by their parity is a much more refined sort of a counting that we can try doing. What we can also do is describe their parity with and what I mean by that is that so in this example, given a partition, can I easily say if it's parity, what its parity is, without actually having to compute the total number of things. And the most important is to study how parity behaves with other representation theoretic phenomena like induction and restriction and so on. So yeah, let's start with Specht modules. So what are Specht modules? So I hinted at this earlier that symmetric group representations are indexed by certain combinatorial objects. These are partitions. So partitions are just ways to break up a natural number into smaller blocks. So given a partition lambda of size n, what that means is that the blocks of the parts of lambda that sum up to n. So given a lambda, there is an irreducible representation of the symmetric group on n letters. We'll denote that by pi lambda. And there's a one-to-one correspondence between these two objects. The dimension of pi lambda is the number of standard Young tableau of shape lambda. So what that means is, so if my n is 13 and 5, 4, 3, 1 is a partition of size 13, because you can add up these numbers and you'll get 13. You can represent this partition as a diagram. So you draw squares, you draw an array of squares. So your first row will have 5 squares, your second will have 4, your third will have 3, and the final one will have a single square. So the shape, the diagram, it records this partition. Now, what we'll do is we'll fill these squares up with numbers from 1 to 13 in such a way that the numbers increase when read from left to right on each row and when read from top to bottom on each column. So here we can check. So this row has numbers 1, this column has numbers 1, 2, 5, 11, so they're increasing. And similarly, this row has numbers 2, 6, 9, and 10, so they are also increasing. So such a filling of the diagram will be known as a standard filling of the diagram, or a standard Young tableau on lambda. So now, So yeah, as I mentioned before, the dimension of the representation is a number of standard Young tableau. So now we can again ask if the dimension of pi lambda is even or odd, and can that be easily deduced just by looking at the partition? So there's an old result towards this, which is that if n is 2 to the k1 plus 2 to the k2 and so on, so that's a binary representation. So whenever I'll write it like this, it'll be understood that k1 is greater than k2, it'll be greater than k3 and so on. So Macdonald in 1971 proved that the number of odd partitions of n is just the products of these powers of 2. So if n is a sum of these powers of 2, if I take their products, that gives me the number of odd partitions of n. So how Macdonald proved this is there is a classical formula for the number of for the dimension, and he asked when does this formula evaluate to something odd, and that gave him a nice condition that the partition should satisfy, and then he used a very clever construction to count the number of partitions that satisfy that. But it doesn't the proof is not similar to what we saw for the binomial coefficients, where we group together things and we argue combinatorially that that a certain partition has odd many standard fillings. So I will call that detecting when a partition is odd. So if I have something like that, I can take a partition and using its structure visually, I want to detect if the partition corresponds to an odd dimensional representation or an even dimensional representation. And that is the main problem that I want to answer in this talk. And I will call a partition odd when the number of standard fillings of that partition is odd. I'll call it even when the number of standard fillings of the partition is even. So the protagonists of this investigation, I guess, are rim hooks. So to define them, let me first define what hooks are. So I have the diagram of the partition 5431. I'll try sticking to this partition for the rest of the talk too. So on the left-hand side, I have marked in color what is called a hook. So I start, I hope you guys can see my cursor. Okay, yeah. So I start at this cell, and a hook is just whatever I get by adding all the cells to the right and adding all cells below the cell. So this is a hook. And similarly, I have as many hooks as there are cells in the diagram. Now, corresponding to this hook, I have a rim hook, which is what I get when I take these two cells, which are the extremes of the hook, and I go along the boundary of the diagram to join them. And so I get this, and that's a rim hook. And note that the number of cells in a hook and its corresponding rim hook are the same. And that will always happen. And that number will be called the hook length of the hook. Now, rim hooks are special examples of something called skew shapes. So what's a skew shape? We take a diagram, we take a partition, and we find another partition whose diagram is contained in the original diagram. So here I started with 5431, and in color I've marked the diagram of the partition 44 sitting inside the diagram of 5431. And a skew shape is obtained when I remove 44 from 5431. So I'm left with something like this. So anything obtained by removing a smaller partition from a larger partition is a skew shape. So note that a rim hook is also a skew shape. So this is obtained by removing, say, 52 from 5431. So yeah, a rim hook is an example. Now I'll define something that's called a paving of a diagram. So to do that, first I need a small lemma, which is that if 2 to the k is the largest power of 2 smaller than or equal to n, then there is at most one hook in lambda that has one hook in a partition of size n, whose hook length is 2 to the k. So for example, let's take 5431 again. Now we need to deduce a few things. So the first is that whatever this hook is, it cannot be it has to be it has to intersect either the first row or the first column of the diagram. Because if it doesn't do that, let's say it starts here in this cell, then I can always move to the northwest and obtain a bigger hook that is completely disjoint from the hook I started with. And when that happens, that violates the hypothesis that 2 to the k is the largest power of 2 that's smaller than n. So it has to intersect either the first row or the first column. Secondly, if I have two hooks that have let's have two hooks that intersects the first row, then okay, no, let me say it this way. All the hook lengths in the first row are distinct, because as I move to the left, my hook lengths surely increase. So here it's 1, here it's 3, here it's 5, and so on. So if I have such a hook, if I have two such hooks, they can't both be in my first row. So now the only thing I have left to consider is if I have a large hook like this in the first row and one in the first column. And when that happens, they only intersect in one cell. So again, you can argue from there that it violates existence of two such hooks violates this condition that 2 to the k is the hook length is the largest power of 2 that's smaller than n. So yeah, let's assume that this is true, that there is at most one hook in the diagram that has hook length 2 to the k. So now if n has binary representation 2 to the k1 plus 2 to the k2 and so on, then there is at most one way to decompose lambda into rim hooks of size 2 to the k1, 2 to the k2, and so on. And this is called a paving of the diagram. So for example, if I have 5, 4, 3, 1, the size is 13. So the largest power of 2 is 2 smaller than 13 is 8. So I can first try finding a rim hook of size 8. And there exists one. So I've colored that in pink. Now I can remove these things, and I'll be left with a smaller partition, which will be of size 5. Now the largest power of 2 that's smaller than 5 is 4. And again, in this case, I do get a rim hook that is of size 4, which I've again colored in, and I'm left with 1. So the binary representation of 13, which is 8 plus 4 plus 1, is nicely represented as successive removal of rim hooks of the diagram. But not all partitions can be paved. For example, this is the partition 6, 5, 2 is also a partition of size 13, but again, you can start to start with, we found a rim hook of size 8, we remove it, but we are left with the partition 4, 1, and this does not have a rim hook of size 4. So this partition cannot be paved. So why do we care about pavings? So to understand that, let's try filling skew shapes instead of just diagrams. So a standard filling of a skew shape is again just a filling of the squares of the skew shape in such a way that the numbers increase as we go from left to right, and they increase when we go down a column. So this is a standard filling of the skew shape, because this 3 has no restriction. So this 3 is satisfying the standard condition. This row is also increasing. We have 1, 4, 5. This row is also increasing. This column is increasing. We have 1, 2, and these two columns are also increasing. So this is a standard filling of the skew shape. What is true is that the number of standard fillings of a skew shape whose size is a power of 2 is odd if and only if it is a rim hook. So now, why is that true? Let me give you a sketch of the argument for why this is true. Okay. So there are some possibilities when we have a skew shape of whose size is a power of 2. So let's say we have the skew shape on the left, and we have a filling. And what I've done is I've marked the cells which are numbered from 1 to 4 in this yellowish color, I guess, and I've marked the cells which are filled with numbers 6 to 8 in pink. So what I can see is that the cells that are marked in with numbers 1 to 4, they don't form a rim hook of size 4, while the cells that are marked with number 6 to 8 are filled with number 6 to 8, 5 to 8, do form a rim hook of size 4. And so inductively, if we assume this is true by induction, inductively we can deduce that the number of ways the number of ways to fill this rim hook of this non-rim hook of size 4 is even. And so we can replace whatever filling we have here with one of these other fillings, and we can group up the initial filling with an even sized filling. On the other hand, the other possibility is this, where the first four cells also form the first four cells form a rim hook. The later four cells also form a rim hook, but together they don't form a rim hook. And when that happens, we can do a local move. So what we can do is we can change this into this. And something like this is always possible. If we have 2 4 rim hooks that join together to form a non-8 hook, then we can always do a local move and change it into another such decomposition. And what this means is that whatever filling we had before, we now have 2 of those, because that's clear, right? I hope. Maybe I should have explained this better, but anyway. On the other hand, if we do have an 8 rim hook, the property that it satisfies is that we can uniquely partition it as a 4 hook plus a 4 hook, and those 4 hooks can be again uniquely partitioned into 2 hooks and 2 hooks, and then those 2 hooks can again be partitioned into a 1 hook and a 1 hook. So that determines a unique filling of an 8 rim hook. So this means that everything else is grouped up like we discussed before, but this one is not grouped. And this is very similar to what happened with the binomial coefficients, where when we do have when we are computing n choose r, where r satisfies the condition we talked about before, the filling, the collection of all fillings, they get nicely grouped up, except one possible filling, which corresponds to when all circles are either are completely filled or completely empty. And that is how we reduce the oddness of the binomial coefficient. Similarly, here, in these 2 cases, every filling that we do, we can group them up into even groups. While for rim hooks, we can still do that, except this filling. This filling cannot be grouped into an even sized partition. So what does this tell us? So what this tells us is that a partition is odd if and only if it can be paved in such a way. So let's see why. So we have 13, which is again 1 plus 4 plus 8. So we start with filling this. So if we fill 1, so we have to fill 1 in here. Then we fill 2, 3, 4, 5. Now in this case, the way we fill 2, 3, 4, 5 is that we get a 4 rim hook. But if you had filled it in any other way, then we would not be able to create this 8 rim hook with the remaining 8 elements. And that would mean that by the lemma that there is a way to permute the filling in such a way that we get an even number of fillings. So the only way to So the only way to get something that cannot be permuted is to respect the paving. So we have our paving, and then corresponding to our paving, we have a unique way to fill the rim hooks that cannot be permuted, and that proves that the partition is odd if and only if it can be paved.
I have a question.
So,
Yeah.
Why can't I permute 3 and 4 in this?
Yeah, so you can. So yeah, yeah, so you can permute 3 and 4. That will give you a different diagram. But what I meant is, so I did not mean that we cannot permute them freely, but the idea is that, okay, let me go over this in a little more detail then. Maybe
The
that will
colors
make it.
definitely can't permute.
Yes.
Okay.
Yeah, they can permute. Yeah. Oh yeah, the colors definitely can't permute, but what you asked is a good question. So I'm not allowing any sorts of permutations. What I'm doing is I am grouping together different fillings into even sized groups, right? So how that is working is that if I have so it's an inductive procedure, but let me describe it in a non-inductive manner. I really wanted to have access to. I really want to draw some things, but I couldn't figure out how to connect my iPad to my laptop. But I'll try explaining it verbally. So let's say we have a partition. Let's say we have a diagram. Okay. Now, this filling can be interpreted as successively adding boxes to the diagram, right? So we start with 1, then we start 2, then we add a 2, then we add a 3. So we get a chain of diagrams. Now, we have 1, 2, great. Now 1, 2 is a domino, right? 3, 4 is not a domino. So technically, we can get a new partition by just switching 3 and 4. And when we continue on, eventually we'll still get a standard filling, right? The problem is that okay. So what we do is we start with 1, and then 1 is done because our binary representation had 8, 4, and 1. So once we got the first power of 2, we stop there. Okay, so we were done. Then we start with the second power of 2. So we go up to 5. So again, whenever we have so 2, 3, they form a domino, so they are sort of frozen. Then 4, 5, they form a domino, so they are frozen again. Okay, so 3 and 4 are not allowed to interchange. What we want is after each step of size 2, we want a domino. Okay, so because if we do change 3 and 4, what we'll have is not a domino. I hope that's clear. Let me actually give you an example of a maybe I had a filling that did not work. Okay, yeah. So let's look at this filling. So here 1 is 1. Now 2, 3, they don't form a domino here. So here I should be able to change them. Okay, so 2, 3 can be changed, and 4, 5 can again be changed, can again be swapped. I hope that's clear. So this inductive procedure, this recursive procedure that I talked about will eventually boil down to this, is the point. This local move that I've mentioned here, the switching at the level of 2 rim hooks, which is just a domino. If you have a skew shape of size 2, which is not a rim hook, they have to be disjoint, and then in that case, this local move that you get is just switching of 2 things which are 2 cells which are not connected, and that's basically what you pointed out. But we can't do that here because we have to look at 2, 3, 4, 5 as our 4 hook, and they're switching there 2, 3, and so there this is a rim hook, and we can't do that. So okay, So yeah, this was the detection theorem where given a partition, all we have to check now is that if it can be paved. If it can be paved, then it's odd. If it cannot be paved, then it's even. So this is what we were, this is what we wanted. Now, why did we want such a thing? So the Young's lattice is a graph which records how diagrams are contained within other diagrams. So the empty diagram is contained in the diagram 1. Now 1 is contained in these two. And then this is contained in these two, this is contained in these two, and so on. So this is the Young's lattice. Now, if we have a partition, we can ask if it's even or odd. And so on the lattice, we can look at the subgraph of partitions that correspond to even partitions. I'm sorry, that correspond to odd partitions. So it's a theorem of Iyer, Prasad, and Spallone that every odd partition in the Young's lattice has a unique odd child in the Young's lattice. So let's look at it in the picture of the Young's lattice we have here. So this row is odd because there's only one way to fill it, which is 1, 2, 3, 4, and it has a unique odd child. What's more interesting is this hook, which is also odd because it is a 4-rim hook, and it has 2 children, but this one has two standard fillings. So it also has a unique odd child. Similarly, this has a unique odd child, this has a unique odd child, and this has a unique odd child. And it's a theorem that every odd partition has a unique odd child. And a question is, can we identify this unique odd child? And that is so the proof of the theorem in their paper is not equipped to answer this question. They also start with the formula for the number for the dimension, and then they get conditions on when a partition is. They get new conditions on when a partition should be odd, and then from there it follows that given an odd partition, it can only have a single odd child. But it's not very well equipped to identify what is this unique odd child. And the hope is that understanding things by grouping, like we did, will help identify this unique odd child. This is still open. We've not been able to answer this question. But the reason why we expect something like this to work is if we go back to the beginning and we go so we go to the binomial coefficients. We know that n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. So if n choose k is odd, then exactly one of these two smaller binomial coefficients has to be odd. And it's again a similar question to identify what this unique odd child is. And this description really helps in doing that. For example, if we have 13 choose 5, and we want to ask if n minus 1 choose, if 12 choose 5 is odd or is 12 choose 4 odd. So how we'll answer this is, if the smallest power of 2 that appears in both of them is the same, then we can subtract 1 from each of them, and we'll still retain this property that the powers of 2 that show up in one also show up in the other. For example, here the smallest power of 2 appearing in both 13 and 5 is 1. And so we can remove 1, and we'll still be left with 4 plus 8 for 12, and we'll be left with 4 for 4. So in this case, the child that is odd is 12 choose 4. On the other hand, if the smallest power of 2 that shows up in R is bigger than the smallest power of 2 that shows up in N, then we should just remove 1 from N and not remove anything from R. And so this description really allows us to easily deduce which child is odd. And the idea is that The idea is that this investigation of the parity of the number of standard fillings by grouping, which is similar to what we did for the binomial coefficients, will help us in answering this problem. I'm not sure how it will work exactly, but in certain cases, it does seem to suggest what child will be the odd child. Second interesting thing about these is that we can ask about the asymptotics of the enumerative problem, asymptotic analog of the enumerative problem. So suppose n is 2 to the k1 plus 2 to the k2 and so on. That's its binary representation. We can compute the proportion of partitions which are odd. And the way we do that is by dividing this number, which comes from Macdonald's formula for the number of odd partitions, by the total number of partitions, and this is P of n. And so here we have a product of log n many terms, because the number of terms here are the number of digits in the binary representation, which is at most log n. And each of these, so k1 is again the largest power of 2 dividing largest power of 2 smaller than n. So that is also at most log n. So we have that the numerator is at least 2 to the log squared n, while the denominator is a partition function which grows exponentially quickly. So this shows that as n tends to infinity, the proportion goes to 0, which means that as n tends to infinity, 100% of, or almost all irreducible representations of the symmetric group are even dimensional. This seems to be quite common. This phenomena shows up in the irreducible representations of the simple Lie algebras. It shows up for the finite general linear groups, etc. And it's an interesting thing to think about if there is a representation theoretic reason for this. If there is a combinatorial reason for this, because in a lot of these cases, these things they count some objects. And is there a reason why for when n is large, the number of these objects becomes more and more even? And yeah, so that's my talk. But I seem to have a lot of time left. So I did have some extra slides prepared that did not make the cut. So let me just talk about that. But maybe I'll take some questions because the extra slides are about something else.
Okay, let's thank Varun for this amazing talk.
Thank you.
Yes, as he said, questions.
So I have a question.
Yeah.
So at the end here, you mentioned that as n gets large, almost all irreps are even dimensional. I'm wondering, is it intuitive to you whether it might also be the case that, for example, as n gets large, the dimension of almost all irreps are divisible by 3?
That is true. So that is true.
Like it might be true for all primes. Like maybe
prime. It's also true for all prime powers.
I see. Okay.
It is, and not just for the symmetric group, but for all these other cases too. That is true. But yeah, it's not intuitive to me at all why the even case should be true too.
So I wonder if you sort of, knowing that, if you could ask for like a higher degree of detail and say something about the growth rate of the expected power of each prime, for example.
What do you mean by the expected power here?
Oh, I mean, so like a typical representation, you expect its dimension to be divisible by any of these primes. How many times do you expect it to be divisible on average, and what is the distribution?
I see.
Something like that.
That makes sense. Yeah.
And if you could, it might give some kind of clue as to like what the combinatorial reason is.
That is true. So what? Yeah. So the only thing I have, the only heuristic I have right now, which also doesn't seem to really work, is that in all these cases, so yeah, when I say irreps of simple Lie algebras, what's going to infinity is the rank of the group. So is the rank of the algebra. So not really the size anymore. So it's SL1, SL2, SL3, and so on. So, and yeah, complex simply algebra. So in all these cases, what we have is there's a natural way that the nth group or algebra sits inside the n+1, n+1st group or algebra. And maybe there's some restriction stuff going on where restricting the representations at the nth level to the n-1st level. And then because at the n-1st level, we have enough even dimensional ones, maybe that's forcing a lot of them to be even dimensional at the nth level. But that's sort of the only heuristic I have. But again, I'm not sure why that would work. But what you said is interesting. I shall think about it. Expected. I mean, do you know of any places or do you know of any places where that has been done before? Things
No,
like
I have no idea. This is the first time I've thought about it. I was just wondering if something's known.
Okay. Right. No, because
I know of like 2 or 3 references, but I don't know how well they go with like what's the. I mean, they definitely show that it goes to 0, but I don't know what they use in the middle. I know like 2 or 3 references, but they're all for symmetric groups also. I don't know.
But they go to 0, yes. But what's the
Yeah. What's the route they use? I think they use like how fast it goes and then show that function goes to 0. I believe they do that, but I don't know. I'll have to check.
I mean, if it is the case where, you know, maybe it's related to some kind of like restriction property, then maybe thinking about it in terms of some like, you know, random walks on the Young lattice or something like that is a fruitful thing where, you know, maybe there's some stopping time where like after some event happens, anything else that you can get to after that is always going to be even or is always going to be, you know, divisible by some prime. And then maybe you can talk about like when that's likely to happen.
Yeah. That sounds right. Yeah. Something like that should work. But the problem with restrictions is that what you end up getting are sums of dimensions, and then sums are not very robust to parity. You can always add an odd thing and just destroy the parity. You can change evens to odds very easily by adding something that's odd dimensional. So, so yeah, that seems to be the only. I mean, I don't want to say the only thing that's common between these things, but for example, cyclic groups or any abelian group again does not satisfy this. We have a family of abelian groups that won't satisfy this. So there seem to be so there's something special about these classical families of groups that people have been studying because this seems to be true, and this is one thing that's special about them. But I'm not sure. There could be many more reasons. So yeah, what I intended to talk about today when I sent my abstract to Aditya is about GLNC irreps, and I did not do that because I thought it would take a lot of time to even make sense of the question because there's infinitely many representations. But yeah, there's a very interesting. I mean, because we're talking about the asymptotics, there's a very interesting enumerative problem that can be formulated here, which is that we have the dimension formula for the representation, and it's a polynomial in the parts, and it is integer value. So for any integer input that we feed into this, the output is an integer, and this implies in general any integer valued polynomial will have its values mod to periodic. So as a function from the integer lattice to z mod 2z, it will be a periodic function. So we'll have a fundamental domain, and so that the value of the polynomials on the fundamental domain determine its values on the entire lattice, and we can try enumerating inside the fundamental domain. So that sort of a thing can lead to a nice enumerative problem that people can study. The problem is that we lose the original combinatorial interpretation of what we are counting. So initially we had partitions, and now we have partitions, but whose but we are now only interested in the parts mods a certain thing. And why is that interesting? To start with, we had all partitions, but now because of this periodicity, we can chop off the parts at a certain size, whatever the period is. And why is that combinatorially interesting? So yeah, finding a combinatorial interpretation for these asymptotic results seems to be slightly tricky.
I had a question, although I think Sheila did too, so I'd like her to go first.
Oh, thanks, Mark. Yeah, very nice talk, very interesting. I was wondering, so does this tell you, since you're using rim hooks or border strips, does this tell you something about the parity of the character values? Can you do that too?
I've not tried that yet, but do you know if the character values have okay, there is the yeah, I mean, probably.
I mean, what you're basically doing is dividing it up into border strips or rim hooks, whatever.
True.
So, yeah.
Yeah, I've not. Yeah, this particular thing is something that that I've not really spent a lot of time thinking about. Just my goal was to just understand why. It was just to answer this question of when is it odd, but yeah, that's interesting. I should think about that.
Yeah.
So
in particular, actually, what I was interested in was the parity of when the parity of the character value is the same as the parity of the dimension, which this might tell you something about that.
So can you refresh my memory? How does the lemma work?
Yeah, so the Murnaghan-Nakayama rule is if you're evaluating the value of the character of lambda on some cycle type, say mu, then you're just going to fill this with mu1 1s, mu2 2s, so that they all look like rim hooks. So that all the ones form a rim hook, and then all the twos form a rim hook, right? And then you just count how many different ways there are of filling your lambda, and there's a sign, and the sign is -1 to the 1 less than the number of rows that a particular I occupies. And then you multiply all the signs together, and that's called the sign of your rim hook.
Okay.
So when you add all that up, it's in Macdonald, and
right.
That would be the character value.
Right. And so from there, the hope would be to deduce a condition for the character value to equal the dimension, is it?
But to have the same parity as the dimension. Yeah.
Same parity as a dimension. Okay, got it. Right. I see. Yeah, I'm not sure, but yeah, I should think about that. So the character value at any permutation or at a
this works for any permutation.
For any permutation.
Yeah. In any conjugacy class, of course.
Right.
If I'm not mistaken, that's the origin of all this rim hook business. Macdonald calls them border strips.
I see. So so the thing is, with this particular problem, I came across this in a very roundabout way. So what happened is I just wanted to understand so a much weaker thing to prove is a much weaker thing one can show is that if the partition is odd, then its core has to either be empty or has to be just a single block.
Mhm.
And to do that, what we can do is we can basically apply the Bender-Knuth involutions for 1, 3 for all the odd numbers. So that corresponds to the domino thing that I was trying to explain. So you start with, so let's assume that we have even many boxes, and so we look at the diagram that we get when we look at the numbers up to 2, then up to 4, then up to 6, and then up to 8. And at each step, if you're adding a domino, then that's sort of the unique length 2 path in the Young's lattice that we can take from the previous step if you're adding a domino. And if you don't add a domino, then there are two ways to go up. And we can locally just switch. We can just take one path instead of the other, and that gives us an involution. And that proves that unless your core is empty, then you'll always be able to do this local switch leading to an involution, and then your thing being even. So if your core is not, and from there, so okay, now we've shown that a necessary condition for being even is that your core should be empty, which means that you can decompose your partition into dominoes. But that's not a necessary condition. That's not a sufficient condition. So what we can do is we can, again, instead of looking at, so earlier we had the diagram written as a union of squares. Now we have it written as a union of dominoes. And now the idea is that can we give an involution on these domino tableau for things which cannot be written as a union of 4 rim hooks. And that is doable. You can always, if you have 2 rim hooks that don't form a 4 rim hook together, then you can again do a local switch which just looks like taking the conjugate partition. And this keeps going. If you have two 4 rim hooks that if you have 2 4 rim hooks that don't together form an 8 rim hook, then you can again do a local switch and get an involution and so on. And that's how rim hooks came there. You start with decomposing into domino tableau and then into domino, and then you ask when can. So if you have 2 dominoes and you look at, so okay, in this case, you have 2 3 and then 4 5. Those are 2 domino, and they together form a 4 rim hook. So that's why you can't do much. But in something that we looked at before, we have 1 2, which is a domino. 3 4 is a domino. So that's good. But then 5 6 is not a domino. So we can switch them. Here it doesn't, you don't see the phenomena that I'm talking about there. But yeah, what I'm talking about is something like this. So if you have these 2 4 rim hooks that are joined together, but they don't form an 8 rim hook. So you can always break this Q shape into 4 rim hooks in a different way, which is like this. And there's always exactly 2 ways to do this. So that's how rim hooks sort of showed up here. But that's interesting that the Murna-Nakayama rule also involves them. So there must be some relation that I have missed just because I was not trying to answer that question. But yeah, very cool. Thank you.
Sure. So I think Mark had a question, right?
I did. So you mentioned that every odd partition, has a unique child. And so you posed that as a question, and I didn't quite check. Did you also propose that you had an answer, or that is an open question for you currently?
No, so what I do have an answer for is, again, so in the Young's lattice, you have, if you just look at the hooks, you get Pascal's triangle. And the discussion on the binomial coefficients in the beginning answers the questions for that subgraph. But in general, my hope is that this method or something like this, maybe a different way to group things up, should answer this question.
So unfortunately, my internet died in the middle of your answering that question.
Oh, okay. Yeah, let me repeat what I said. So what I said is that so we have the Young's lattice. If we just look at all the hooks in the Young's lattice, uh, and take the dimensions, what we get is Pascal's triangle. So we get binomial coefficients back again. And the children that I talked about there, so n choose k is equal to n choose k minus plus n. Yeah, that's exactly the same as the two children that a hook will have in the Young's lattice. And so this question is answered in that for that subgraph, for those partitions, using this interpretation of grouping things up together and then asking what happens to the one that is not grouped. So whatever is not, so we've grouped things up into these groups of even size, and we have a single one that's all by itself. And what we want to do is when we restrict from n choose k to n choose k minus n minus 1 choose k minus 1 or n minus 1 choose k, we want to understand where will this special configuration remain something that's, so we want things which are we want the even sized groups to stay even sized, and we want this special one to be again alone. And that's why I feel that this approach should help answer this question, but in general I haven't been able to.
So the thing that jumped out to me is that it looked like your work, like you were determining whether or not a partition was odd by kind of coming up with a special filling. And I'm guessing, I don't know if I quite got all the details, but essentially you had some kind of involution or involution that fixed exactly one filling.
Yes. Basically.
And so my curiosity is okay, you have a special filling. N has to be on one of the boxes of that filling.
Yes.
When you remove N, do you get the unique child?
I mean, in an ideal world, yes, but it doesn't always happen like that.
Okay.
Yeah, I mean, we can try here. So, okay. Can you still see my screen?
Yes.
If I go out of the presentation, you can still see it?
Yes.
Okay. So let me go to one of my favorite websites for a second. Yeah. I'm not sure if people know of this website. A lot of people don't, but I just love playing with this, with partitions all day long. So 5431. 5431. So there are odd many standard Tableau. We can remove 13, which is this one right here. And it's still odd. Okay. So in this case, I guess it's true, but I am pretty sure it's not true always.
Okay.
I mean, you can keep removing. You might probably find it becomes even.
But I need to write down again what my special solution is, right?
Yeah, like that. One is at 12.
I'll tell you the problem. The problem is that what we would like to do is we would like to take one out from the smallest power of 2 that we have, right? Which is 1 here. But so our small, so the way this works is that our small powers of 2 are concentrated at the top and the large ones are near the border, and we're removing from the border. So this doesn't really respect the paving that we have.
Okay.
So that's the problem that I've found with this approach. So maybe there's a different way to do it where we have the large powers of 2 are all near the top and the small, and so the smallest power of 2 is somewhere on the border, and then from there, then it'll make sense to remove just one from the border. So
sure. I guess if you're looking for that, have you considered just, finding a large odd partition, looking at the chain of children that it has, and just putting that filling in and trying to see if you can understand that filling in that way? Because I mean, every odd partition has its child. It has the odd partition filling.
Yes, that is such a good idea. I don't know why I haven't tried that before. But yeah, I should have. Yeah, okay. That sounds like a great plan. I should do that. Yeah.
Okay. We'll end the questions right now. Thank you. Let's thank the speaker again.
Thanks for the questions. Great questions.
I'll stop the recording.